So now we've learnt how to balance simple half equations. We did that yesterday. Today we're going to look at how to combine different half equations. So I'm going to take three different examples I'm going to take you through. The first one's simple, then we'll get a little bit more complicated, and then we're going to look at like the most complex it can get. So in this first example, you can see we've got zinc as a solid, and the zinc is turning into zinc 2 plus, so I can tell straight away it's going from elemental zinc, so oxidation state 0, to oxidation state 2 plus, which means my oxidation state is increasing and it is being oxidized. I can also tell this because the zinc is losing electrons, so this is an oxidation reaction. And I can also tell that the other half of the reaction that I'm going to combine it with, I've got silver ions that are aqueous. They're going to gain electrons, and they're going to go from being oxidation state +1 to being oxidation state 0. So we're gaining electrons, and our oxidation state is decreasing, so this is reduction. So we need to look at how to combine these two equations. So to do that, the first thing I need to do is make sure that the number of electrons that are being produced by the oxidation reaction, which is 2, is going to be sufficient or the right amount to balance and work with the reduction reaction. And we can see we've only got 1 electron being used by the silver. So what I need to do is double everything in the silver reaction. So I'm going to say we've got 2 Ag plus and 2 electrons making 2 solid silver atoms. And by doing that, I'm then going to be able to take the 2 electrons that are produced in the zinc reaction, and they are going to be able to work with the silver reaction because they're going to be balanced. I can then combine the 2 reactions together because the electrons balance. So I'm going to take both sides and write the whole thing out, but I cancel anything that appears on both sides. So I can see my 2 electrons are now able to be cancelled, and I can write out the full reaction. So the full reaction is going to be 2Ag plus aqueous plus zinc solid making 2Ag solid, so 2 silvers plus zinc 2 plus. Little note about terminology before we go any further. So if our zinc is being oxidized, the zinc must be our reducing agent because it reduces the silver. The silver is currently in oxidation state +1 and it's turning into silver 0. It is being reduced, therefore the zinc is acting as a reducing agent, and we can say that the silver on the flip side of that must be turning the zinc from zinc 0 to zinc 2 plus. So the zinc is being oxidized, so the silver must be acting as the oxidizing agent. Now, as you can see, this is a slightly more complex example. So we're starting off with iron. Iron being iron 2 plus, so oxidation state +2, and it's turning into iron 3 plus, so oxidation state +3. Its oxidation state is increasing and it is losing electrons, so it is being oxidized. Okay. And the reason this is a more complex example is because we're going to be doing that oxidizing using the oxidation state manganate. Now this is normally, we normally use this in potassium permanganate, which is like a bright purple substance. And when potassium permanganate gets reduced and acts as an oxidizing agent, it goes from being manganate 7, which we can see at the start, MnO4 minus, to manganese 2 plus, or oxidation state 2, which is colourless. And we use manganate an awful lot in redox titrations, which is where we can do a titration and we see a nice clear colour change. The manganese then, this is obviously, it's gaining electrons. It's going from +7 to +2. So its oxidation state is decreasing, so it's being reduced. So this is a more complicated example because we've got the waters and the hydrogens and a much more complex thing to balance. Right, if we have a look at how to combine them then, we can see we're going to produce each ion when it gets ion when it gets oxidized produces 1 electron. Now the manganese or the permanganate ion requires 5 electrons for it to be reduced into manganese 2+. So we can see what we're going to have to do is we're going to have to multiply our first reaction, the ion reaction, is we're going to need to multiply by 5 so that we get enough electrons to be able to power the reduction of the manganate turning into manganese 2. So if we times this by 5, we can have 5 Fe2+, 5 Fe3+, and 5 electrons. We'll end up being able to balance those 5 electrons. So we end up with 5 electrons on the left-hand side, 5 electrons on the right-hand side. So we can cancel those out and write the whole thing out. So we're going to end up combining the equations. We'll end up with MnO4 minus, so the manganate ion, plus 8H plus 5 Fe2 plus, turning into Mn2 plus 4H2O plus 5 Fe3 plus. So now I'm almost out of room, but I should just go back and add in the state symbols. So manganate is aqueous, the hydrogens are aqueous, this is going to be aqueous, water's obviously a liquid, and so this whole thing's happening in solution. Right, so this is our whole combined equation. We can see we've no longer got any electrons in it, so it's not a half equation anymore, and everything is combined. Final points to note then. So our manganate ions must be, they are being reduced, and they are the oxidizing agent. And the Fe2 plus is being oxidized, and it must therefore be the reducing agent for the manganate. So the manganate gets reduced by the ion, so the ion is doing the reducing. So we say it is the reducing agent. It's a little bit back to front because I know you'll be thinking, so the thing that is oxidized is the reducing agent, and the thing that is reduced is the oxidizing agent. So we come on to our most complex example because there's going to be more to balance than just the electrons. So let's have a look at how to do this. So we've got, first of all, we've got the dichromate ion, and the dichromate ion is going from being chromium 6 to being chromium 3. So in dichromate it's chromium 6 plus, or plus 6. In chromium the oxidation state is plus 3. So we can see we're going from 6 to 3. It is being reduced. The oxidation state is getting lower. So this is being reduced. Okay, in our hydrogen peroxide, the hydrogen peroxide is going from being, the oxygen in it is going from being -1. If you remember, I told you before that in a peroxide the oxidation state is the only thing where oxygen doesn't have an oxidation state of -2. So our oxidation state in hydrogen peroxide is -1, and it's going from being -1 to being elemental oxygen, which is 0. So we can see our oxidation state is increasing, so it's being oxidized. Now, to combine these two equations together, I'm going to start in exactly the same way as I was doing before. So I just need to look at making sure that the number of electrons is balanced. So I can see I've got 6 electrons in the first example, and I've only produced 2 electrons in my oxidation reaction. So I'm going to need to multiply everything in the second equation by 3 so that I get enough electrons. So if we put a 3 in front of the hydrogen peroxide and a 6 in front of the hydrogen ions a 3 in front of the oxygen and a 6 in front of the electrons, then I'm going to have enough electrons to be able to power the reduction reaction. So then I need to combine the two reactions together. So I need to go through and cancel out anything that appears on both sides. So if I take another colour, so I can see that the 6 electrons, they're going to cancel. Excellent, I don't have to write those out. So we can start writing the whole thing out. We're going to have Cr2O7 2 minus, which is aqueous. Now the next thing in the reaction is the 14H plus, but I can see in the oxidation reaction I've got 6H plus on the right hand side. So I need to take those 6H plus away from the 14H plus. So if I cross off the 6H plus from the right hand side equation and I take them off of the hydrogens I've got here, so 14H plus take away 6H plus is going to be 8. So we're going to make that into 8. So this is going to be plus 8H plus, which is aqueous. We've cancelled the electrons already, so then we just need to add our 3H2O2, which is a liquid. I forgot to put the state symbol in before. And then that is going to make, I'm going to run out of space, I'm going to put my arrow underneath because I haven't got enough space on the screen. That's going to make 2Cr3 plus, which is aqueous, plus 7H2O, which is a liquid, plus 3 oxygens, which would be a gas. So the last thing to do is just to look and say what's the oxidizing agent, what's the reducing agent. So the dichromate gets reduced, and I know that dichromate is quite a commonly used oxidizing agent, so it is our oxidizing agent. And the hydrogen peroxide is therefore, and I haven't really got room to write this in, I'll write it above it, is our reducing agent. Now I'm going to finish up just by talking about a final bit of terminology. So we've talked about reducing agents, oxidizing agents, how to tell if something's being oxidized, how to tell if it's being reduced. And how to combine the equations, etc. There's a final bit of terminology you need to be aware of, and this is a nice, lovely, new long word for you. It's disproportionation. Now, disproportionation is when something is simultaneously oxidized and reduced in the same reaction. Now, it can be reasonably easy to spot. You can see when one species appears just as one thing on one side of the equation, but that it seems to get split and appear in two different molecules on the other side of the equation. So I've got an example here where chlorine reacts with hydroxide ions to form chloride ions, chlorate ions, and water. This is what happens in forming bleach. This is what most household bleaches are, in fact, a mixture of chlorine and sodium hydroxide. So the ionic equation for that, if you take out the sodium ions that would be spectating, would be this. Now, if we have a look at the oxidation state of everything that's involved, should be able to see the pattern. So chlorine as elemental chlorine, its oxidation. So let's write this at the start. Oxidation state. So it's oxidation state 0. In the hydroxide, we know that the oxygen is -2 and the hydrogen is +1. Okay, and then we've got, in the chlorides, we've got -1. In chlorate, we've got oxygen is -2 and chlorine is going to be, so we've got 3 -2s is -6. It's got to add up to minus, so it's got to be +5. And then in water, the hydrogens are +1 and the oxygens are -2. So let's have a look at what's happening with the various different parts. So let's deal with the oxygen and the hydrogen first. So oxygen starts as -2 and finishes as -2 and everything. So oxygen is definitely not being either oxidized or reduced. It's staying in the same oxidation state. Hydrogen is +1 at the start, and it's +1 in water at the end. So the hydrogen is not actually taking part in any redox. The hydrogen's oxidation state is not changing. But if we look at the chlorine, it starts off as oxidation state 0, and it finishes on one side as oxidation state -1. So it has gone from being 0 to -1. It has decreased, and if it decreases, it means it's being reduced. But at the same time, it's also turning into oxidation state +5. So it's going from 0 to +5, so it's being oxidized. So in reactions where one species gets simultaneously reduced and oxidized, and it forms two different molecules or two different species with the same thing in, and then we call this disproportionation. There are various other versions of disproportionation, but I'm just going to leave it at that for today, I think.